We have calculated principal stresses, and or we have given the expression for principal stresses, as you see here. The question is, how can I find these sigma 1 and sigma 2 in terms of radial and polar coordinates? And this is our expression for principal stresses, sigma 1, 2. They are found. Can you close that door, please? Can you close the door? And the expressions for sigma xy and xy, they are given. Suppose that these are equations 1, 2, and 3, sigma y, sigma x, sigma xy. And sigma zz is also given. That's one of the principal stresses. And now I can find sigma 1, sigma 2, sigma 3 in terms of radial and angular coordinates. Substitute stresses in port to find, and after a modification or simplification, you can find sigma 1 and sigma 2. If you substitute the asymptotic expressions, we are going to find sigma 1 as k1 over square root of 2 pi r cosine theta over 2 times 1 plus sine theta over 2. That's sigma 1. And sigma 2, the other principal stress, is k1 over square root of 2 pi r cosine theta over 2, 1 minus sine theta over 2. Sigma 3 is also required for Mrs. Yield criteria. Now, if you go back, it's given here. Sigma z, we know that sigma z is sigma 3. And therefore, I can also write sigma 3, which is a conditional function. It is 0 for plane stress, and 2 nu times k1 over square root of 2 pi r cosine theta over 2 for plane strain. Now these results are found, and we have to substitute these for Mrs. Yield criteria. In other words, use sigma 1, sigma 2, and sigma 3 in for Mrs. Yield criteria. And now at this point, we can substitute it into von Mises Yield criteria and solve the resulting equation for R. And it is going to give you the location of the point at which yielding occurs. Therefore, solve for R, the radial coordinate. And you'll find two separate solutions, one for plane stress and another one for plane strain. I can write down these results. These are the boundaries of the plastic zone. And the first results are, we are going to solve on Mrs. yield criteria for R, and R is obtained as a function of theta. Is equation. It's K1 squared over 4 pi sy squared times 3 over 2 sine squared theta plus 1 minus 2 nu squared 1 plus cosine theta for plane strain. And what does this tell? This gives the locus of points at which yielding occurs, or yield condition is satisfied on this curve. And if you assume that sigma 3 is 0, you'll be able to find R of theta. Again, this time for plane stress, R of theta is, problem is mode 1, K1 squared over 4 pi sy squared times 3 over 2 sine squared theta plus 1 plus cosine theta. And this is for plane strain. Sorry, plane stress. Two separate results for plane stress and strain. And as you see, they are found. And this represents the size of the plastic zone, and we can show it on a diagram. This is generally plotted, but a normalized plastic zone size is defined. Plastic zone size is defined. I'm going to show it as R star. R star is R over K1 squared over pi sy squared. A normalized quantity. And normalized coordinates can also be found. For example, R star cosine theta is, let's say that this is X star. It's actually X over K1 squared over pi sy squared. And the next one is R star sine theta. Let's define it as Y star, and this is Y over K1 squared over pi sy squared. These are defined, and they can, now R star can be plotted. For example, consider plane stress. R star here is R over K1 squared over pi sy squared. It's 1 over 4 times this function of theta. I can plot it as a function of theta and show it in the correct plane. And we can do this for both plane stress and strain. Suppose that this is the crack tip, and I'm defining. Let's try it again. It's crack tip. When you plot it, you can generate a plot with a Met software. You'll get two different curves. One for plane stress, and another one, somewhat smaller one. Significantly smaller locus of points. The larger one is for plane stress. And smaller is for plane strain. And this is Y star, this is X star. I can see R theta or R star is defined on that line. Now, what does this tell us? Under same conditions, plane stress plastic zone size is larger, significantly larger. I can quantify it. Less amount of plasticity observed near the crack tip under the condition of plane strain. These numbers can be calculated, for example, on the crack plane. What is the size for plane stress and strain? For plane stress, go back to this result. For theta equals 0, this 0. For theta equals 0, this term is 0. And you'll have 1 plus 1. And you'll get 1/2 on the right side. Therefore, this is theta equals 0. This is 1/2. And if you do that for plane strain, what's the coordinate of this point for plane strain? If you go back to the original result for plane strain, if you substitute 0 for theta, this is 0. But you need to specify Poisson's ratio for plane strain, and let's say that it's 1/3. If Poisson's ratio is 1/3 and theta is 0, you will get 1/18 here. Plane stress is 9 times larger. Now this curve or the other one, that is the locus of points on which yields condition is satisfied. Therefore, on the curve, yielding occurs. What about outside of this zone? This point, for example, did it yield or not? No yielding outside of the zone. This is non-yielding zone. Therefore, the regions lying within these curves are named as plastic zones because stresses are larger inside. If it yields on the periphery, it definitely yields inside the curve. Now, these are used in different applications related to fracture mechanics. One of the observations is that plastic zone size is larger for plane stress, and I can write down the equations for theta equals 0 and for plastic zone size, choose size for theta equals 0. Calculate. We have already calculated this. The factor is 1/2. Therefore, R of 0 is going to be shown as RP. And this is K1 squared over 2 pi SY squared for plane stress. And if you evaluate this for plane strain, you'll find K1 squared over 2 pi SY squared times 1 minus 2 nu squared for plane strain. And this second one depends on Poisson's ratio. You see that there is a significant amount of difference between plastic zone size. And that has certain implications regarding fracture behavior of specimens with different thicknesses. If the specimen has a large thickness, we have a case similar to that of plane strain. If thickness is small, then there's a case of plane stress. But we will talk about these in more detail. Any questions about these final results regarding plastic zone size? Okay, now let me stop the recording at this point.